Yes, this is how the Earth looked. The oceans were completely frozen, or nearly so, multiple times and for long periods. The most recent Snowball Earth started about 850 million years ago and lasted some 200 million years. Of course, this was devastating for life on Earth, but did you know that all of this ice destroyed the mountains and mercilessly ground the continental rock right down close to sea level? This process created the Great Unconformity. Why, hello and welcome. The Great Unconformity and Snowball Earth. I mean, what a title. That is a dramatic title, and for good reason, and we will be learning about that. Before we embark on this journey of seeing the actual rock of the Great Unconformity and putting our hand on the outcrop and doing field geology and discovering it together, I thought it'd be very important to do just a quick tiny lecture on what an unconformity is. Let's start with depositing layers of rock through time. From the bottom up, of course, okay? Just layer upon layer. Now, I like to think this is like pages of a book. This is what's recording the rock history, the rock record, the record of the Earth. And so we have just a continuous, in the optimal situation, just a continuous record. It just continually deposits new layers of rock. Now at times, because of the mountain uplifting or the seas receding, these layers of rock are no longer being deposited on top of each other, but erosion comes in and erodes out some of the record. So I'm going to take a little rag here, and here we go. I'll just maybe erode it out like this. Now there's a new surface of erosion like this, okay? And then new layers, which I'll put in red, and it goes on again, okay? And then we can have erosion again. But each time there is erosion and then deposition on top of it, we have an unconformity. And that's the beauty of the outcrop behind me. It shows very clearly the elements of an unconformity. The red rocks of the Chugwater Formation were deposited some 250 million years ago. Then they were uplifted and tilted about 65 million years ago, and erosion occurred, forming the unconformity surface. Finally, new deposition occurred as travertine deposits within the last 10,000 years or so. This means that there are about 250 million years of the geologic record missing. Now, I want to make it clear this is just one unconformity of many, many, many in the rock record, and it is not the Great Unconformity which we will be focusing on. In the end, the principle of an unconformity is pretty simple. As I've shown, pages of the book, meaning layers of rock, have been eroded, and we no longer have that history to look at there, do we? Because it's been destroyed through erosion. Let's go into the beautiful Shoshone Canyon and see the Great Unconformity. Well, here we are at the Great Unconformity, and I mean the Great Unconformity. First of all, let me point out the actual unconformity. It's right up here where you see kind of a cup-shaped, dish-shaped bottom. That's the bottom of a river channel. Right along here, okay, I can't quite reach it. And underneath it are granites that are 2.7 billion years old. So when you take these sedimentary rocks that are 540 million years old, and underneath it are granites that's that old, the 2.7, that's over 2 billion years of time that's missing right on that contact. Well, one thing that's really cool to do is put your hand on the contact. Let's walk this unconformity and follow me here. Let's follow this contact. You can follow it pretty easily. You can see it. We're coming down. It's coming down. This beautiful pink granite. Here it comes, and right here I can put my hand on that contact. So we come right down to where the unconformity comes to where I can touch it. We have the granites here, the pink granites right here, and right here are the sandstones. So that contact is right here where my hand is, and that's that great period of missing time, the Great Unconformity. Let me tell you, it's pretty exciting for a geologist anyway, to put your hand right there and think about everything that has occurred during this period, during this missing time period of 2 billion plus years. We know that there were multiple episodes of mountain building, and some of the mountains were ginormous, like the Himalayas. We know that there were periods of glaciation that lasted hundreds of millions of years and created what we call Snowball Earth. Just amazing to think about all this that happened during this gap of time, right here. Our next stop on this journey is the wonderful Wind River Canyon, just south of Thermopolis, Wyoming. I've drawn the blue dashed line to show the general dip of the formation layers as they come up the mountain. The white dashed line is the trace of a massive fault, which I'll be discussing on the whiteboard. Well, before we head into the Great Wind River Canyon, I wanted to show you a sketch to help you understand what we're going to be seeing on drone video and understand the geology a little better. For reference, this represents the river that goes through the mountain. This is that cuts through the mountain. The town of Thermopolis is back on this side to the north. And on the south, on the other side of the mountain, is Shoshone, the town of Shoshone. So for reference, these are the layers of rock, of course. This is the huge fault that brings up basement clear way up from great depths. I want to say there's 20-some thousand feet of displacement that has been lifted up on these rocks. And we're going to drive up the river, and you're going to see these dipping strata, these dipping layers, which means we're going to drive into older and older rock as we get further and further up the river into the canyon. And finally, we will come to the Great Unconformity, which is represented by this red line right here. So just a general idea. The dips on here are I've exaggerated a lot on this sketch. It's really only somewhere like 15 degrees of dip, the big layers. This layer of rock or formation is the Permian Age Phosphoria. As we cut deeper and deeper into the rock, we come to the Pennsylvanian Age Ten Sleep Formation. Further into the canyon, we see the Mississippian Madison Formation, the Ordovician Bighorn Dolomite, and shaly limestones of the Gallatin and Gervant formations. Up around the bend, we will finally come to the Flathead Sandstone and the Great Unconformity. Finally, we've arrived, and I'm looking at the beautiful Flathead Sandstone overlying heavily weathered granite. The Great Unconformity is right here. As we continue to cut deeper and deeper into the mountain, I want you to pay attention to the unconformity and what is underneath it. Here we see beautiful pink granites. Moving along, we continue to see granites under the unconformity. Often the unconformity is difficult to identify because it is not a sharp contact. I'm starting to see a change here. Do you? Do you see this layer of dark-colored rock here next to the pink granites? Let's turn the camera 180 degrees and look directly across the river to the other side of the canyon. Indeed, we see dark-colored metamorphic rocks that have been intruded by these granites. And here we can clearly see the Great Unconformity with some granites and metamorphics underneath it. Can you see the layering or layers that are within the dark metamorphic rocks? I really like this view because we can see these fingers of granite, this light-colored pink granite intruding into the metamorphic rocks. Often the layers within these beautiful metamorphic rocks dip steeply. Turning the camera to look yet deeper into the canyon, we see that the canyon walls are dominated by dark-colored metamorphic rocks. The red dashed line is approximately where the unconformity is. Note the steep dips on the beds or layers. Well, now that we've seen this amazing video and made some observations with the drone and about the metamorphics and the granites and everything, I wanted to use the sketchboard to help us understand the context and the geology. So what I have sketched here is the world 2.7 billion years ago, more or less, okay? The mountains, massive mountain ranges were around in Wyoming. Granites had intruded. They had eaten their way into the rock through a process called stoping and other processes where the granite intrudes. Sometimes it kind of squeezes in, other times big chunks of the metamorphic rocks get worked in and cave off and spall off and cave off into the hot molten rock. Now this granite is about 20 million years younger than the surrounding rocks that we observe today, the dark-colored metamorphic rocks. And here's the amazing thing is to be metamorphosed, these rocks, and for this granite to be there, this was about easily 15 miles deep, buried about in this area. Some 15 miles underground, that granite cooled. So the Great Unconformity hadn't occurred yet, but now the process started. The mountains were uplifted and over eons of glaciation and not all glaciation, some rivers and rain during periods started eroding off the mountain. So I'm going to take a rag here as a big eraser, and we're going to use that as erosion. And erosion started occurring and going. So 2.7 billion years ago, 2.5 more or less, started eroding down through time. Of course, it was very rugged until it got closer and closer to sea level, and then it started flattening the terrain out, okay? Here it is, through time, through time. And this red area represents the granite, as we'll recall, and it eroded some 15 miles deep. Let's just put a line right there, okay? That is the Great Unconformity. Now, as you notice, I have granites over here and metamorphic rocks over here from the ancient mountains that are preserved, right? But we're not finished. So we eroded it all down, and some 530 million years ago or so, the oceans, the warm oceans came back in. And as the ocean came in, the Flathead Sandstone was deposited right on top. And then the ocean just kept getting deeper and deeper and depositing more and more layers of rock. So here we go. Layer after layer of rock that we saw as we came into the canyon with the drones. Some 11,000 feet of rock were deposited. And then the new mountains, the Laramide Mountains, the mountain that created the canyon that we came up through, deformed all this yet again. To represent the Laramide orogeny, I'm just going to tip my board here. So now it all got tipped, like we observed. And then the canyon came through and cut it all out. Wow, what a sequence of events, huh? So I want to focus in here, right here. What we observed with the drone is first we were in the granites, downriver to the north, which is towards Thermopolis, on that side of the mountain. And then we got into a boundary area, didn't we, where we saw granite mixed with metamorphics. And then as we came further and further up the river, it became completely dominated by the metamorphic rocks. It turns out in the Wyoming provenance, there's this mix of batholiths, huge bodies of granite, and then terrains of metamorphics. For instance, the Bighorn Mountains, about half of it is metamorphic on the southern end of it. The northern end is dominated by granite. In the Wind River Mountains, we have two major plutons of granite, but we also have vast areas of metamorphic rocks. So it was a very complex mix of metamorphosed rocks, sedimentary rocks, and volcanic rocks that had been turned into metamorphic rocks through burial. And then the granites coming in and intruding and invading, shall we say, all that. I realized I needed to make something a little more clear to us. And that is this idea of metamorphic rocks being buried 15 miles deep, or the granites cooling off 15 miles deep and then being eroded down to it. How does that work? Okay, this is phase one, and that is we have a basin full of sediment. This is a cross-sectional view with my little tree here. This red area represents a granite intrusion, okay, into the metamorphic rocks that we've seen. And it's way down deep, 15 miles under the ground, where you get this metamorphism. It's not just 15. It can easily be 15. It might be a little less, or it could be quite a bit more, okay? But very deep. And that's where this occurs. And then uplift starts to bring these up to the surface, and that'll be phase two. So phase two is you bring these rocks up high through time. They're being squeezed and compressed, and bringing them up to be eroded. Now, as mountains are uplift, erosion is occurring and they reach an equilibrium. So you can only get mountains about so tall. I mean, Mount Everest is just shy of 30,000 feet, if I remember right. So you have a maximum and the erosion keeps up, and you keep bringing those deep, deep sediments that we had on the prior sketch get up above sea level, okay, eventually. They get up above sea level as the erosion occurs and keeps coming up, and they work together, okay, erosion and the rising of the mountains. Now, early on, for the longest time, they're big, tall, rugged mountains. It's early after the uplift, and it brings that up, and you keep eroding down. So continuing on in this journey of erosion of these mountains, now we've taken it clear down. We've eroded these mountains way down. Here's sea level right here. I've symbolically shown these metamorphic rocks. I could put granites in here too, but we've eroded some 15 miles easily, 15 miles of rock to get down to this point, okay, in the core of the mountain. And notice the relief that I've depicted here is very gentle compared to the rugged mountains that we get early on, the big, tall, rugged mountains that we've seen. And it's a natural process. As you get closer and closer to sea level, you have less and less relief, which means less energy, less potential energy. Studies have been done here in Wyoming to show that the relief here, the tallest hills are only like 150, 200 feet tall, and they tend to be more gentle and broad, okay? There's a modern example of that situation in the Canadian Shield. That's what we see. Everything is down close to sea level and has really been eroded down over a huge amount of time. We've learned a lot here in the Wind River Canyon, but believe it or not, it has one more very important piece of Earth history to reveal to us. Well, I've mentioned a couple times about the warm ocean waters that came in finally and deposited the Flathead Sandstone. And you might ask, well, what evidence do you have for that? And that's a fair question, of course. And that's what I love about this outcrop right here. This is the Flathead Sandstone right here in the Wind River Canyon, right above the Great Unconformity. Let's go take a look at it. Okay, so here we are. Let's take a look here, right where my hand is. See, these looks like spaghetti in the rock. Just spaghetti hanging down. These are worm burrows, vertical worm burrows. These tubes are called scolithos. We don't know exactly what the animal looked like, but they were worms. This outcrop is completely full of them. Just pretty amazing to think about, because these worms like to burrow vertically in high energy environments, like right on the shore face, right at the beach where the water swashes around. That's where these worms dig vertically down to stay away from the high energy so they don't get washed away, right? And they dig down and feed on the organics within the sand on the beach. So how did warmth arrive? What caused that warmth to come and melt all these glaciers and bring warm water to the world? Well, the best theory we have is that there was a period of intense volcanism which put tremendous amounts of CO2 into the atmosphere and helped us warm up. I just love this outcrop. It's the best outcrop I've seen for these vertical tubes, scolithos. And it is direct evidence that the whole world had changed, that warmth had arrived, and that life had begun to flourish and would continue to explode in diversity and ultimately, of course, lead to, well, to us. Well, I want to take you to a really special place. It's a bit of a drive. It's an 8-hour drive, actually. And it's to Antelope Island in the Great Salt Lake near Salt Lake City, Utah. And there's some special deposits associated with the Great Unconformity. I think you're going to like this. This is what it's all about right here. This is why I drove all these miles, 8 hours, and fought a snowstorm and was in 3 hours of traffic jams to show you this outcrop. Let me show you some details here. If we come right up here and look at this rock, it has some very surprising features. So now that we've moved in a little closer, I'm hoping you're starting to get excited like me looking at this rock. I mean, you have this beautiful black background color, which is a shale or mudstone. It's very dark colored. It's what we call a matrix. And then you have these clasts, these angular clasts. Some of them are kind of rounded as well. They're kind of stretched. That's because they've been squeezed and metamorphosed. That's an entirely different discussion. That isn't why I'm here with you. But all these various shapes, and they're beautiful. They're made of quartz and various granite types here. This huge clast up here is quartz, very large. There's something odd about this, for geologists anyway, and that is we have a complete mix of clast size. We have the very fine-grained mudstone shales, then we have clasts that get huge. This is very unusual and can only happen in two ways, one of two ways. From debris flows where you get lots of rain in the mountains and it's in a muddy, shaly area and it breaks loose and now you have mud, and then it can go over areas that have rocks and all kinds of stuff, and it all mixes it up. and then it deposits at the bottom of the mountain, okay? Those are debris flows. The other way is deposits from glaciers. Okay, now glaciers, they don't care. They grind up rock into really fine flour. They carry huge rocks on top of them, and within them and underneath them. They push them. I mean, they don't care about size of rocks at all, okay? Unlike a river, which is very particular. And in fact, most depositional systems sort out the grain sizes really well. And so this is why it's so unusual for geologists. Now this formation is called the mineral fork tillite. It's 2,000 to 3,000 feet thick. And this is the neat thing. You can tie it right back to the Great Unconformity. The Great Unconformity is above it a ways, okay, not too far above it. But these are deposits from these giant continental glaciers that I've been talking about that have eroded the entire continent right down to the roots. This is the direct evidence of these glaciers that were depositing this. And in fact, geologists have been able to go around the world and see these kinds of deposits at this age that near the equator or at the equator, and that's why they start to go, oh boy, you know, this probably means, and the more we study it, the more we think that the earth was entirely ice covered, snowball earth, or nearly so. There's some debate about how much and all that. I don't want to go into those details, but essentially let's just call it snowball earth. So my trusty whiteboard with a sketch to help us out, okay? This black line represents the Great Unconformity as it was being formed, okay? This blue here is a big, huge continental glacier that's eroding everything down and has eroded it right down to sea level, okay? The wiggly lines here represent metamorphic rocks where it's ground down into the core of the mountains, just taking them right down to the roots, right down to sea level. Here's sea level. This is not well done. This blue line here, the wiggly blue lines is the ocean water, okay? We have these huge icebergs that just break away off the front of the glacier as it reaches the ocean. So we have the glacier, and incorporated within it as it's tearing up these mountains is all this debris I'll put in red. All the debris on it, within it, underneath it, in front of it, on the side, you know, wherever it can, okay? And it's carrying it out, and it finally gets over this hinge point and starts heading into the ocean. It starts dropping all that rock that's within the glaciers, and also, I'm sure, pushing some out too into these low areas. But most of this here that we've been looking at is more dropping out of the glaciers as they melt, the icebergs. And this red wedge here represents what we've been seeing here, the mineral fork tillite. Now this wedge, as I've said, of the mineral fork tillite that we have recorded here in Utah is some 2,000 to 3,000 feet. I mean, that's pretty spectacular. And it's these rocks dropped into the shales. These dark shales are the ocean sediments. You know, it's very quiet water. And you deposit very fine-grained shales, these black shales and mudstones, okay? And then the glaciers bring in all this rock. Some big, big boulders can be, very large size. And dropping it in there, and that's why you have this really bizarre situation where you have very low energy mixed with very high energy, meaning very fine-grained stuff, rock, mudstone, shales, mixed with very high energy rocks. And you can do that, of course, with these glaciers. So eventually, as the earth warmed, the glaciers melted, of course, started to melt. That, I'm sure, took a long time. Sea levels started to rise, bringing in sandstones across this Great Unconformity here that we've seen in Wyoming, the Flathead Sandstone. The very same sandstone that's equivalent here in Utah is called the Tintic. And in the Grand Canyon, it's called the Tapete Sandstone. And over in the Dakotas, it's called the Deadwood Sandstone. But they're all the same, okay? Bringing in this sandstone on top of here. So a point I want to make here is in Wyoming, this rock underneath the Great Unconformity is some of the oldest on the continent. You have to go to the Canadian Shield to get older, but it's 2.7 billion years old. And the sandstone, the Flathead Sandstone, is some 530, 550 million years old, so you have a huge gap in time. However, as you come over here into Utah, this unconformity is underlain by, well, this mineral forktillite we've been looking at and a couple other thinner units, and they're around 700 million years old. So that the gap in time is much less. And in the Grand Canyon, the rock underneath is some 1.7 billion years old instead of the 2.7 that's in Wyoming. So how do we get changing gaps in time along the Great Unconformity? How does that happen? Okay, so I have my sketch here. This piece here represents continental crust, the real old stuff, Wyoming. Good old Wyoming, right? 2.7 billion years old. And this represents oceanic crust that has plunged in a subduction, has plunged down underneath another piece. So they come together, right? The oceanic crust comes, meets, and it plunges underneath like this. That's plate tectonics. You can study up on that a little more. Sometime I may do a lesson on that. But anyway, it subducts. This whole plate goes underneath, plunges underneath, starts melting, and that material works up and builds volcanoes. We call this a volcanic arc. And there's a lot of sediment associated with shedding off these volcanoes and everything else. But see, what's happening is they're coming together through time. And eventually this material, this volcanic arc, and all its associated sediments hit Wyoming, the old craton, and these are younger. So for instance, the terrain that's in southwest United States that includes the Grand Canyon, it's one of these 1.7 billion years old, and it hits Wyoming. And Wyoming is kind of the center of the universe. Everything is accreting onto it, sticking onto it as it comes around, building the North American continent. Amazing. So this comes and hits here. Now you have 2.7 billion year old rock, and once this hits it, you have next to it, that's stuck onto the side here, we can think of it, that's glued together, sutured together, is 1.7 billion years old. So now you have dramatically different ages of rock next to each other, right? Let's revisit the rock and be right at the outcrop, and we can put our hands on it, or at least I can. I sure wish you could with me here, because you can just feel the history in this. Looking one last time out over the Great Salt Lake shrouded in a beautiful fog, I contemplate the amazing earth history of this area, which overwhelms me with a sense of awe. Well, we've made it here to an overlook of the last stop. We're going to be stopping down below in this country, way down here, for the final stop to wrap up this Great Unconformity discussion. But I wanted you to see this overlook so that you get an appreciation for the vastness of the country, and hopefully you'll see how amazing this place is to see the Great Unconformity. So let's just take the drone right down here, right way down below to the tops of those canyons to give you a broad scale feel for where the Great Unconformity occurs here. I think I see the unconformity now. Do you? Here it is, with the beautiful Flathead Sandstone above it and the pink granites below. Let's move on to a new area. These beautiful rugged canyons have been cut deep into basement rock granites by the Clark's Fork River. In most of this area, the Flathead Sandstone has been eroded and stripped back along the Great Unconformity surface. This happens because the sandstone is easier to erode than the underlying granites. This means that all these relatively flat areas along the canyons are the actual unconformity surface. Try to imagine this surface uncut by canyons extending as far as the eye can see. That scene is much like the world looked as the glaciers receded. Well, now that we have a better understanding of this broader region, let's go ahead and drive down, way down there, onto the rim of the canyon down there and have our final discussion. Well, here is the Flathead Sandstone. I'm standing just above the Great Unconformity, so I'm going to walk along here around the corner. We're going to look at a couple things at the sandstone. First of all, I want to look right here and just look at all the beautiful cross-bedding, we call it, in the sandstone. I've drawn a few blue lines here to help guide your eyes so you can see this cross-bedding or cross-stratification. Those are along the fronts of the bed forms out in the ocean waters, typically less than 200 feet of water, where you get these foresets, these cross beds coming in. Someday I'll do a lesson on that, a lecture on that. And I'm just walking down through the section, down a little deeper into the sandstone, a little deeper, getting ever closer to the Great Unconformity, and come right around here, around the corner where the parking is for the cars. I'm going to come right around the corner. In fact, the flat area where you see the cars parked is the actual unconformity surface, and this is where the Flathead Sandstone has been stripped away by the process of erosion. Here is a view of the same parking lot from across the river. The steep canyon walls are the granites underneath the Great Unconformity surface. The Flathead Sandstone is back in the trees, back behind the parking lot. And as I come around the corner, you can see how this sandstone weathers naturally instead of the road cut that we were just at. Typical weathering pattern of this beautiful sandstone. Well, I've finally made it to this surface. I'm standing literally on the surface of the Great Unconformity. My feet are on granites here in this area, granites that are 2.7 billion years old. I've got the sandstones that are 550 million years old or so behind me, and it's being eroded and receded and stripped back that direction behind me to reveal this surface. Now, I've been talking about some big numbers in time, and I want to help you understand deep time. I think that's critical when we're talking geology. So let me get something here. I have this book, and I think this is appropriate because books record history. We use them to record our history. Let's imagine for a minute that each page in this book is 1 year. Each page is 1 year. Now, I've been talking about 500 million year old sandstone, a little older. How thick would this book be with 500 million pages? Any guesses? Well, it turns out it's 40 miles. This book would be 40 miles thick. Now, I've talked about 2 billion years of missing time on this surface. That's, well, it's easy to do the math. It's about 160 miles thick this book would be. That's just the missing time on this surface. Wow, it's rather overwhelming. Okay, I want you to think of something, to really think in your minds creatively and imagine This surface is being eroded back right slowly. And if I dig down with this handy little garden trowel, I am revealing the unconformity. Just bringing it back, right? And I could keep going back a little, and I am revealing this unconformity, which hasn't seen the light of day for some 600 million years. Wow. As I walk along this amazing surface, I ponder the massive amount of the rock record that was relentlessly eroded away by huge glaciers. And I imagine a barren strip of land with absolutely no vegetation of any kind. Then I see an ocean in the distance with a beautiful beach, and I think about the miracle of the warmth that arrived. And now I want to walk right over to the beautiful sandstones deposited by this beach that came in as the ocean rose. Right into this beautiful sandstone. What joy this brings to me to think about the life, the warmth, and the life, the explosion of life that occurred, represented by these sandstones, which ultimately led to you and me to be, and for me to be right here. I've mentioned a few things about sea level rising, glaciers receding, and all this, and I wanted to show you this sketch to help put it all together. This is so important. This is a cross-sectional sketch with the glacier here, okay, represented in the blue. The land surface, the Great Unconformity at the time, so this is some 550 million years ago, is this black, heavy black line, okay? This is a pluton of granite that has intruded into metamorphic rocks. So these black squiggly lines represent the metamorphic rocks that we've seen. I'm going to put a line right here for the moment. That's the ocean, okay? That is the ocean at the time as this glacier receded, the sea level is rising. Now, I want to mention this pluton. Remember, it was at least 15 miles deep when it cooled off. So we know that the erosion by these glaciers and primarily the great glaciers eroded down some 15 plus miles down to, it just erode the continent down, right? Now as these glaciers melt, sea level is rising. So here's time one. Time two, as we continue to raise sea level. And guess where the beach is? It's right here, huh? If you were to walk on the beach. So let's pretend like I'm standing right now on this Great Unconformity right here. Okay? So as sea levels continue to rise, they're coming my way. The beach is coming my way. And the sandstones are deposited. So here we go. Through time. Oh, finally got my feet wet, huh? And keep going. And actually, sea level, as these glaciers melted, sea level rose to the point where it essentially covered the entire continent of North America. Wow. So now that we've seen in cross-sectional view what happened, I want to show you in map view what the world looked like. It turns out that the gentleman that created these maps that I'm going to show you, his name is Dr. Ron Blakey. And I studied under him for my graduate work. In fact, he was my advisor for my thesis. And it was a great privilege to work under him. And he's well known, very well known, because of these maps. You see him in museums and in many publications. Probably the best known geologist on the planet right now. So let me grab these maps here and show you. Okay, here's the first map. This represents during the deposition of this Flathead Sandstone, or actually, yeah, right after or right during deposition, some 500 to 550 million years ago. This is the state of Wyoming, heavily outlined here in black. Okay, and this is all of North America, the continent of North America. And this is the western edge of Idaho. So you see, we had a lot of North America that still didn't exist at the time. So the deeper waters were out here, and as these glaciers melted, the water started encroaching and coming in. and coming into Wyoming and depositing the Flathead Sandstone and other formations above that as the water continued to get deeper and deeper. Let me show you the next map here. So here's the next period of time, some 50 million years later, is in the Ordovician. So this is when the waters had come up to their maximum, and you see most of all of North America had been covered with shallow seas. Another reference point, by the way, this is Hudson Bay here. And we're getting down, here's the panhandle of Texas to give you a feel, okay, for the lay of the land. So here, North America, unlike any other time, was covered in water, in shallow seas primarily. Thank you for watching this video. I hope you've enjoyed it. And I hope you'll enjoy some of the other videos I've made and those that I make in the future.